All right, so actually talking about geology now, finally. Handful of you may have seen this slide, well, the next couple slides, while I was getting things organized. Excuse me. And it was in display mode, or presentation mode, whatever it's called. So you might know some neat little fact about these rocks that we're going to talk about in a minute. But otherwise, we're going to play along just like the folks at home that have, they're like, okay, we're looking at a picture of rocks. So, looks like, what? Desert somewhere, right? Utah, California. Just a cowboy movie, maybe. You got some rocks, you got some sand and dirt, and you got a sky. Well, that's great. That's what you want to see. But what we're looking at here is the layering in those rocks. All right. What kind of rocks? And don't say nice, because we're just learning about metamorphic rocks in lab, and they're banded and so on and so forth. But what kind of rocks are layered usually? Sedimentary rocks, right? We've said over and over again, sediment gets deposited in layers, just like dust on your shelves in your house. Sediment piles up. Soil horizons, you might have heard of that word. Okay, soil piles up in layers. Yep, I am recording. Just wanted to make sure I was recording. So sediment piles up. We're used to that. Sediment, then, sedimentary rocks, then, are an environment. They are a snapshot, like we're looking at here. They're a picture. They're a whole damn photo album. Okay? And as I often say in lab, when we're looking at a hunk of fossiliferous limestone or something like that, you've got the front of the book and the back of the book when you look at the top and the bottom of the rock. And then all those layers are pages in between, right? And when it's in that context, sitting there in a lab room or on somebody's shelf, or just a random picture on the internet, we don't really have any way of determining if that each layer is a month, a week. You don't know how intense the environment is, so on and so forth. When it's in situ, as they say, in place, in location, in its original location, like this, it is a bit easier. There's a handful of rules that they've made over the years that pretty much seem to work out no matter where we go on the planet, that help us decide without even doing, chemistry and stuff, radiometric decay, we're not even talking about that. Saying which part of this is oldest, which part is youngest, and we'll talk about some of that. And then, of course, as I said, radiometric decay, nowadays, heck, last 100 years even, we can throw a little part of a rock into a machine and look at some of the isotopes in there, and maybe not 100 years, but find out, roughly speaking, how old it is. The older it is, the bigger fudge factor you have on either side. The younger it is, generally the least amount of margin of error. But they've gotten quite good. So they've got two tools. And as it turns out, that second tool, where we actually get a solid number, supports all of these seemingly weird little rules that they made up before they had machines. So we're getting pretty good at it. And what we know then is that there are a couple environments on the planet that make layered rocks. You can be out in the desert, and sand layers up. Sand looks a special way when it's turned into a rock. And I don't just mean sandstone, but sandstone from a desert looks a certain way. You can make it at the bottom of a lake, or the bottom of an ocean. It layers up sediment. We talked about sorting the other day. Remember sorting and deposition? We talked about that. So So we know these situations that make rocks. We see them time and time again. So when we see something like this, we can make an inference. We can say, okay, these rock layers are horizontal. This is mud and sand. This was some sort of lake environment. We don't see any limestone anywhere near it, so probably not marine. And then you could start bringing in fossils into the conversation. But we don't see any of that, so we're going to go with just, fresh water. This was a lake. So there's actually a study of that, what we just discussed, and it's called stratigraphy and sedimentation or sedimentary structures. But stratigraphy in particular, strata is layers. Stratus clouds, you might have heard of those. But strata means layers. So it's talking about the rock layers. So when we come across something like this, that's actually on Mars and not in a desert here, this is just a little further along the same outcrop. That first picture was Mars as well. This is why they're saying, okay, there was water here. They haven't found any fish fossils. They haven't found any snail fossils that they're telling us about. They certainly haven't found any little green men or women. But we see layered rocks. We know how layered rocks are made. And at the moment, we have every reason to apply that knowledge to other planets. So planetary geology is a thing. It's a really cool thing. For the longest time, we just had to sort of peek from telescopes. But now we could freaking send robots there to drive around and take pictures for us. How cool is that? All right, and good pictures at that. We want to send people there. Yeah, I get it. That's great. But for right now, this is amazing stuff. There's not a whole lot of lag when we're controlling them, and it's been amazing. We've been poking around on Mars for a while now. Not everything worked out. Been a handful of different rovers, Pathfinder and whatnot. All right, but we've got some amazing studies done. So yeah, sedimentary rocks on Mars. Therefore, at some point, there was very similar environments to what we have here. So the next question, of course, comes up, usually, if you're engaged at all in this conversation. Well, what happened? Mars is a good bit smaller than us. As such, it had a hard time keeping an atmosphere. Remember what holds an atmosphere to a planet? What? Gravity, right? Gravity is a function of mass. The more mass you have, the more gravity you have. So the gravity on Mars is a good bit lower than here. What atmosphere they did have didn't stick around very long. More than likely, there is plenty of frozen water there. It's very easy to keep it if it's cold. But the running, flowing water that made these rocks very, very, very long time ago seemingly is long gone, at least so far as they're telling us. So, short story long, okay, not only does the stuff we're talking about here apply to you as you're wandering around through the woods, driving around on the highways and looking at rocks and so on and so forth, quite seemingly it can apply to our solar neighbors as well.
Have they found fossils?
Not that they're acknowledging. There were some peeps for a little bit about some organic compounds, and they went back and forth about whether or not they could be biological in origin. You have to think about evolution and how long it took us to get where we took. So if we're going to apply the principles of stratigraphy to other planets, we also have to apply our other scientific principles as well. I believe we briefly talked about solar nebula theory in here. the idea that the planets are all roughly the same age. So, in acknowledging that as well, we have to then figure out how long Mars had an atmosphere in order to support life. And that's the part where they're not sure yet, / not telling us. They could date these rocks, and I'm not sure the dates that they got on them. But sedimentary, again, as we've mentioned, is a pain in the butt to date because it's pieces, parts of 1,000 different rocks, right? So whether or not they ever tell us about fossils on Mars, and then eventually, if they did find something, I'm sure they'll tell us eventually. Everyone wants them to, right? It's probably going to be really sort of invertebrate stuff. I'd be surprised if they ever got past seashells. If evolution works the same way there as it does here, which it probably did, you got to look at that evolutionary ladder and then the length of time that they had to do so. We didn't talk about it in here because it's more of a historical geology class, so you talk about that. But we go about 3.5 billion years before we got pond scum. So
They don't know how long ago Mars was.
right. But I'm just saying, again, let's assume that they have the same birthday. Okay. It took, like I said, 3.5 billion years to get pond scum here. We're closer to the sun, a good bit warmer. We have better atmosphere, arguably, so on and so forth, sort of in that Goldilocks zone, as they call it. And again, a step further out, we'll see. At the very least, they're going to have micro stuff.
Yeah, you said
But
something about organic compounds. I read something where they said that they saw, like they were like debating it, but they thought it was fossilized bacteria.
yeah, it's tough because a lot of things can mimic. Sitting in the shelf in the lab room, I have a pyrite. What the hell do I call it? I'm just going to call it a disc right now. A pyrite disc that you would swear was a sand dollar. We were talking about sand dollars the other day in lab. Remember that? You would swear it was a sand dollar, except that we find them in totally non-aquatic environments, let alone marine environments. It just happened to grow that way. So the same thing with the bacteria. The bacteria tends to form. I don't know if you guys remember we talked about. You need to by the final. The stromatolites, the layers of bacteria in the mud, that could also form just totally on its own. And this is where it would be nice to have a human there, and really digging at and backing up, because sometimes we could program these things to take pictures of this, that, and the other, grab a sample of this, but sometimes you just need to back up, sit down, have a beer, and think about stuff, and that's really hard to do this way. So, while it is amazing, it does have still its obvious limitations. But yeah, and there's going to be people arguing both sides of it forever until we find something entirely conclusive. But yeah, I would say most definitely there's going to be something microbial kind of stuff. But getting up into the more complex critters, I doubt it. I'd be surprised if it got past seashells and stuff like that. But we'll see. One day we will be there because we're going to trash this place. So we'll go live in little tubes and bubbles on Mars, just like all the sci-fi books told us we would. But all right. Anyhow, so this isn't about speculative astrogeology. There's the word I was looking for. We're going to bring it right back down to earth here, literally. And this is about layering of sedimentary rocks. Just when we got those images, it was really amazing. Like I said, let alone not just the clarity, but the fact that if you've ever been out west, that you would say, and I am by no means one of those people who thinks the moon landing was shot in Utah or whatever, but I could totally, seeing stuff like this say, Okay, yeah, they just went out to Arizona and took some pictures. But they didn't. Yeah, so the one, and this is the opening slide. I just was coming back to that this is Mars. There is, if you guys are on, I know it's on the Facebook, it might be on Instagram, and you guys have probably gone past Instagram anymore. But there is, they put up at least once a week a 360 panorama, where you like move your phone and it changes what's on your screen. These panoramic shots from the rover that's up there now. Some of the vistas, the sites are just amazing. Just amazing. Most of them like right out of one of those Clint Eastwood spaghetti western movies from the early 70s. Just mind-boggling, the similarities. So to recap, sediments are deposited in layers. All right? Now, the new part, we call those layers beds. Bedrock. You've heard of bedrock, right? So we call these layers beds and or bedding planes. I will never use the word bedding planes again. I promise you that. I typically call them layers. Occasionally strata. So bedding is visible layering within the rocks. All right. Your best example of that would be thinking of the shale that we saw in lab, or the fossiliferous limestone. If you had that piece where you guys could see all those layers really nicely. You can see it in sandstone. Sand grains are fairly uniform. It's tough. Oftentimes, with sand, you're dependent on maybe a little bit of color change here or there. But any of the sedimentary rocks, arguably, could show this. And what's more importantly here is that they should be flat, just like your notebook in front of you, your textbook, whatever, a deck of cards. They should be flat, horizontal layers, which tells us that anytime we see something that isn't, been driving down the road and you see all the layers are up at 45 degrees or something silly. Just make up a number. Or they do a little roller coaster thing. All right? We know that that doesn't happen unless something happened to that rock. Because think about it. If you were a little grain, let's think of that roller coaster-y one where there's ups and downs and ups and downs, all kind of bends in it. If you were a grain of sand sitting there in the water, what are you going to do? Gravity still works in the water. You're going to roll downhill. So we don't get deposition on slopes. So that slope would arguably never even build up. You get a pile, again, of horizontal stuff down in the nook, in the bottom, in the valley, right? So in order to get those hills, they had to have been straight first and then bent. All right, so here's a great example. And again, we're kind of dependent on color to separate stuff out for us. If you were up closer, you could probably see. But tan, black, some of that might be shadowing. When you get down into the whitish gray stuff and you see those black bands, that's definitely not shadowing. These are probably sandstones and shales, if not sandstone and a wee bit of limestone. I wasn't even talking to you, you silly one. And here's the other cool thing, again, if you dig this, is that we know from studying it that certain environments make certain sequences. So we can look at this and then say, oh, this was that environment. It's really like CSI stuff. I don't know if that's still a popular show or not. I never watched it. But these folks that show up in Sherlock Holmes, whatever you want to reference, you show up at a site, something happened, and they look around for clues to figure out what happened. All right? That's what this is. And if I haven't mentioned it yet, this is my end, finally, of geology. I didn't do minerals and igneous rocks. And I mean, I had to learn it, but this is where my interest lies. As I always say, surface processes and critters. All right. So this is something that I might tend to ramble a bit on, even more than usual. So I apologize beforehandedly. All right, so our first of the silly little rules. Principle of superposition. They're all going to be principle of something or another. You guys had earth science in high school. You should remember at least hearing all of these. Whether or not, how you did on the Regents, that's in your hands. But you have been exposed to all these, I'm pretty sure. So superposition tells us that if you're looking at a layer of rocks, the oldest rocks are on the bottom and the youngest rocks are on top, if nothing's happened to it yet. If you think about it, this one makes a whole lot of sense. In fact, this approaches what we kids used to say in the 80s, well, duh, okay? And a lot of these are well, duh moments. But somebody had to be the first one to say, hey, this applies to this situation. I usually use the Daily Mail as an example in this. So let's say, for whatever reason, because of the way you come and go at your house, you're in charge of bringing the mail in, right? And if you're like most families, there is a place you put the mail. Dining room table, coffee table, kitchen table, wherever, counter. You always put the mail more or less in the same place, right? So Monday comes along, you find the bills, you leave everything else there, throw it in the pile. Tuesday comes along, pull out what you need, you throw everything else in the pile. Wednesday, Thursday. So come Saturday night, you're like, let's get some pizza. Hey, didn't there a pizza coupon come in the mail the other day? Yeah, and then you get your conversation you're having with yourself or whoever. Yeah, I think it came Monday or Tuesday. So you go to that mail pile. Are you going to look on the top of the pile or are you going to look on the bottom of the pile? Not rhetorical, folks. Bottom of the pile, thank you. But why is it on the bottom of the pile? Because it's been there longer? Yeah, pretty much. It was there first, right? That's all they're saying. So what they're saying is think back to that cliff we showed. Well, here, I'll just go back to that cliff we showed you. Where's the oldest rocks at? At the bottom of the pile. How come? Because they were there first. But somebody had to point that out, or we couldn't use it as a rule. Okay? It's really silly. It's really straightforward. But it's really helpful if you know it's a rule. So that's superposition. They do have that little asterisk. Well, that's not an asterisk. That's the bullet. But that little, in an unaltered section. Now, if your dog comes along, we were talking about dogs a couple minutes ago, and knocks the mail off the table, and you put it all back together, put it on the table. Where's that pizza coupon now? God only knows, right? Could be in the middle, could be in the bottom, could be right on top. It's a big mess. Now, we don't have giant dogs that come around knocking sediments around, but we do have faulting, cracking, earthquaking, plate tectonics, all that stuff that does mess with the rocks. And again, generally speaking, we can tell. Every so often, they'll do something incredibly crazy, like completely flip a section upside down. It happens. It's rare, but it happens. And that's where you'll see eventually we need to have a combination of the two. Not just these principles, but good old-fashioned science and technology. So again, here. I was lucky enough to take this picture, if you can believe that. There's some beautiful stuff out west. So we see these layers here. Again, you can see the layers. Everything's the same color, but you can still see the layers. This is probably a function of cementing, right? We talked about how rocks are compacted and cemented. Why you get these little ledges here or there. They were just glued together a little better. They're a little more resistant, so on and so forth. Next rule, principle of original horizontality. Spell check does not like that word, I can tell you that. This one tells us that in an aquatic environment, I didn't mention that earlier. In an aquatic environment, sediments are deposited in horizontal layers. So if you recall on one of the earlier slides, I told you that sediments are almost always deposited in flat layers. A lot of our depositional sites are aquatic. You can get some land deposition, of course, don't get me wrong. But a lot of the stuff we see is aquatic in origin. And again, this is due to gravity. All right, it will roll down a hill. And even on land, stuff rolls downhill. But certainly you've seen soil on a slope before. So you know that you can acquire sediment. So now when you look at a cliff, you should know that if it's not horizontal, it should have been originally, as long as it's aquatic. And also that the oldest stuff is at the bottom and the youngest stuff is at the top. So next time you're driving by, down the thruway by Little Falls there, and you look at all that shale, you now know two more things about it in addition to the fact that it is shale. So again, one of my pictures. I am not leading, I promise you that. So when we look at that rock basically in mid-ground there, something happened to it. Because the rock in the background is definitely horizontal. Especially comparatively speaking. If it were on its own, that'd be a tough call. But looking at that layer, okay, there was definitely some shifting going on there. And even that boulder in front of it. It's always hard to get my mouse to move in this mode. That boulder right there is slanted. So it came all the way forward. So something happened. Oops. Sorry. All right. I'm not going to mess around with it. Something happened between those horizontal layers in the back and these diagonal layers in the foreground here. There must have been some sort of fault or something. And again, if you were a geologist that cared about that, you would be out there looking for that fault. Another principal. Lateral continuity. We're going to ignore the parentheses for a moment. So we're just going to read it without the parentheses. A rock layer extends out in all directions until it ends. Huh? Okay. Sure, that makes sense, I guess. A rock is until it isn't, and then it's not a rock. All right. That is the definition, believe it or not. When we put the words in the parentheses in place, and we go back to the fact that I was trying to get across to you guys earlier, that a layer of rock is a representation of an environment. All right? And look out the window, look out your window at home. At some point, look out a window and look at the environment that you're in. And let's just say you're somewhere near the end of a street or by a park, and you've got a field. And at some point, that field turns into a woods or forest, right? And then somewhere on the other side of that forest, well, at this point, there's probably a neighborhood or something like that. But you get my point. We see these transitions in nature all the time. If you go back and say that rock layers can be a function of an environment, then we should see those same transitions. We should see, and again, I wove an example of something you're familiar with. They don't make rocks exactly, but let's pretend they do for a moment. You should see then underneath the field, or in the field, whatever kind of rock fields make. And then as we transition into the woods, you should see whatever kind of rock that woods make, and so on and so forth. That rock layer ends and it blends into something else as we change environments. So that's one aspect of lateral continuity, okay, is that the rock goes on until it doesn't, and then it turns into another rock, typically. And that change means you're changing environments. But there's another cooler and actually much more important example that is not illustrated in this picture. That's me. Hi. This hike, I don't want to say damn near killed me, but I had made it roughly at your age, and then I went back 6 years ago and did it with the scout troop. Even though I was smoking, don't tell anyone, like pack and a half of cigarettes when I was your age a day, I hiked through, that's Arches National Park in Utah. It was like 120. I hiked that back then with probably little to no problem. But now as a old man of almost 50 when I did that, it was a unique experience. Let me put it that way. Especially as little girls in the princess dresses and flip-flops were hopping by me on the trail singing. That was not encouraging. So, anywho, it was quite an experience. If you ever get the opportunity to go out west, yes, it's a lot of red rocks everywhere. But it is stuff you just don't get to see here. You really don't. And do it while you guys are young and can actually hike it and enjoy it. So, actually, we could use this picture. I know there's a reason I put this picture here. So this arch that I'm standing under, the rock directly behind me, and then you see way off in the distance, sort of in the right corner there before we hit sky, those extra rocks there. What lateral continuity tells us is that it's all the same damn rock. There's just stuff that happened in between, weathering, a river came through one part, ground it down. Picture the Grand Canyon, all right? You're standing there, you can't picture the Grand Canyon, a big cliff, you're on one side, and there's rocks you could see on the other side, okay? Anything a bridge has ever spanned that you've gone over. What lateral continuity tells us is that you should always check to be sure, but more than likely the rock you're standing on right there is exactly the same rock that is over there. And if it isn't, it's whichever one it should progress into. Because again, Mother Nature can do whatever she wants, but she does tend to do the same things over and over again. Fields turn into woods. Or when woods die, woods turn back into fields. Sometimes, if you get a change in your weather, a field could turn into a marsh, and a marsh could turn into a lake. And the opposite happens, lakes dry up. But, again, it's a repeatable pattern that we've come to observe, and then because of that, we can apply it. This, for once, is actually like science, that stuff we talked about in the very first week or two of class. So lateral continuity. An environment extends out in all directions until it doesn't. At which point there should be another type of rock. Cross-cutting relationships, and as a subset of this, principle of inclusions. Cross-cutting relationships says that the disrupted pattern is older than the disruption. Well, what the heck does that mean? All right, imagine that there's that field again we were just talking about. Now imagine you borrowed somebody's tractor and you lower the cutting deck and you drive through that field and cut a big old swath right across it. What's older? The path you just cut through the field or the field? The field. How come? Because it has to be, right? Yeah. All right. That's all this is saying. So the disrupted pattern is older than the disruption. So whether you take any one of these rocks that we just looked at and put a big old crack down the middle of it, what came first, the rock or the crack? Well, obviously the rock. Let's go back to igneous intrusions. Remember we talked about dikes and sills briefly? All right. So let's take a whole bunch of rock and have an igneous intrusion go into them. Which one is younger? The intrusion. Again, common sense, but somebody had to lay down the rules. So inclusions piggybacks onto this. Think of the hunk of conglomerate you saw in lab. What's older, the rock or any one of the pieces parts inside the rock? The pieces parts inside the rock, exactly. What's older, the nugget or the chicken? The chicken. All right, that's what principles of inclusions tells us. All right, the inclusion is older than what it's included in. Kind of awkward wording, but nonetheless, the same idea. So these guys are different rules, but the same idea. Grab a fireman convention or something out there. So at this point, you may not have noticed it, but we're up to like 6 or 7 principles of, okay? You just sat here and thought how stupid they all were, so don't miss them on the test. That would be 6 or 7 really dumb points to miss. Because wait, there's more. This one's a little different. I actually started the conversation today with this premise. We didn't use this word, but this premise. Oftentimes you hear this just shortened to uniformitarianism. You hear shortened to the present is the key to the past. Okay? What that means is that we should be able to look at what's going on right now and assume's a horrible word, but assume that the same laws of physics, for example, applied in the past. Rain still rained the way it rains now. Rocks still roll down hills the way they roll down hills now. Water still evaporates the way it is. Anything and everything. So processes and rates that occur now occurred similarly in the past. Are there any issues with that, though? Do you think that's a steadfast rule? Well, the environment's definitely changed. And you might need something more than I'm pulling out of it. So yeah, things have changed over the years, but would that change the laws of physics and stuff? Or what are you getting at, I guess? Well, I'm saying, can we assume that processes and rates that occur now have always occurred at the same rates? Is that a safe assumption? Anybody else?
I'd say no.
And how come that?
Because in any process, there's constants and then there's, variables that change. So if you take that into account, then the process can't really be uniform.
All right.
Water always froze at 32 degrees, but there's other processes that there's more involved than just a rule. You know what I mean?
Okay. Well, you're both right. All right, you're both right. Enough stuff is not unchangeable, but fairly similar, that we can at least start with this assumption. But shit happens, to be vulgar about it. But things happen. We may or may not have talked about it, but there was a period of time called heavy bombardment where we just got hit with way more asteroids and meteorites than we currently do. Thank God for that, right? But that is no longer a constant. It certainly had an effect on things. Sedimentation rate, maybe not. But other aspects, yeah. Maybe it rained a whole hell of a lot more 300 million years ago than it currently did. We certainly know that cycles happen. In my environmental science class, I'm constantly harping about this. Mother Nature, we've got ice logs, core samples that have air in them, air pockets in them. Ice has air bubbles. And you can look at those air bubbles and you can get literally snapshots up to hundreds of millions of years ago of what the atmosphere looked like. And while I'm not saying that, we're not messing around with the CO2 now, we certainly are, but we have tons of evidence that Mother Nature brings CO2 up and down all by herself without anything to do with us over time. And that has brought us into and out of ice ages, all by herself without anything to do with us. So we have these things that go on in the background. And again, we're not, I don't know, I might do geologic time with you guys this semester. Depends. I'll ask you when we're off camera here if you want to keep going down this road or not. But, there are philosophies, for lack of a better word, catastrophism, uniformitarianism, actualism, that debate this kind of stuff. But as a general rule, you need a starting point. All right, think about, you guys aren't necessarily far enough along in any of your majors yet, but the one I always like to talk about is in chemistry, and we talk about the electron shell model. All right, so you're a freshman, you're just learning chemistry, and yeah, you got to learn how these electrons line themselves up in the rings around the nucleus in order for you to do the math, and then 3 semesters later, they whip out this stuff where, electrons, we don't really know where they are. They come and go, and sometimes they're on Neptune, sometimes they're in your cat, and electrons, they're a crazy, crazy thing. Well, imagine if you walked in freshman chemistry 101 and they start with that. Where do you go from there? So you got to have some foundation, you got to have some basis, and uniformitarianism does give us that. You just can't, strictly abide by it, but it is a starting point. It is a starting point. All right, shifting gears. We're done with these foundational principles here for a change, or for the moment. And we're going to talk about the naming of rock formations. This, for once, is straightforward. I'm not used to a whole lot of straightforward stuff in science, let alone geology. So a formation is a group of rocks, okay, that we have some reason to name, some benefit to giving it a name. So somebody's been out there, they've studied it, and they probably wrote a paper or two about it, and it gets a name. So a group of bedding planes of one rock type or a repeated pattern of rock types. That is a formation. Formations are named, as I just said, typically by the location and the rock type. Utica Shale is a great example. All right. Where do you find the Utica Shale? Utica. What kind of rock is it? Shale. Wow, that's incredibly helpful. Thank goodness. Thank you, scientists. It's not often we get something like that. You get that kind of name if it is one rock type. They're not going to say the Utica shale, limestone, and sometimes a little bit of sandstone. They're not going to call it that. If you get a bunch of rocks, then they use just the word formation. The Albany Formation is a great example of that one. The Albany Formation, I believe, is alternating layers of limestone and shale. But it's been a while since I've Googled that one. So you have to go into the works a little bit more. You know where it's archetypally found, but we don't know what kind of rocks it is until we go pull that paper and read it, or at least nowadays Google it. Now, that doesn't mean it's the only place it's found. It typically just means it's the place where it was first studied or the best example of it is. Again, I grew up in Ohio, and I was just leaving there when fracking was becoming a thing. And I was very surprised to find out way after the fact, actually, that what they were tapping in Ohio was the Utica Shale. It's way deep there. Takes a big dive as it comes out of Utica. But that's what they were hitting up in Ohio to get their gas. But around here, it outcrops, which means it's at the surface and is visible. And this is where it was first studied. So it's only later that they applied, well, lateral continuity, really, and said that this formation carries all the way across. So anywho, if you see the word formation in the title, assume it is some sort of pattern of rocks, more than one. And if you see the rock type, obviously, like the Coconino Sandstone is one that's out in the Grand Canyon. What kind of rock is it? It's sandstone. Where do you find the best example of it? Well, Coconino, wherever the heck that is. So on and so forth. Hey, there it is. So the Kaibab Limestone, the Toroweap Formation, and the Coconino Sandstone, and then something unnamed underneath. All right. Now, between each formation, we have what's called a contact. Contacts, as it turns out, are pretty dang important. They're a whole lot more than just seams. What contacts mark are essentially changes in the environment. Because you had to stop making, it's not a factory, all right? So they literally had to stop making limestone and start making whatever is in the Toroweap Formation. And then the Toroweap Formation, they had to stop and start doing all sandstone. Now, because out of convention I just did this from the top down, I actually did it backwards, right? Which one formed first? Yeah, Coconino Sandstone, the bottom one, exactly. So you had an environment that was producing all sand for a very long time. That's rather thick, easily several hundred feet. This is a slight picture of the Grand Canyon here. So several hundred feet of sand. And then I'm going to guess, just by looking, you got limestone above it and sandstone below it, that the Toroweap Formation is either sandstone and limestone, or maybe some shale thrown in there. But we're going to go with, for convention's sake, to make this conversation easier at any rate, we're going to say it's a mixture of sandstone and limestone, and then the Kaibab then is all limestone. Now, what I know that you guys don't know is that sandstone tends to form onshore. Limestone tends to form fairly far offshore. Remember, limestone, we've said this a number of times, limestone only forms in a marine environment. So first and foremost, you're looking at an old ocean. Second of all, you're looking at a part in that ocean where do you find sand right now in those oceans, at least as far as we know? The shoreline, the beach. So you're looking at the rim of an ocean. And this is what kind of bothers me. I'm hesitant to jump from straight sandstone to limestone because usually there's shale in the middle. Think about depositing sediments. You go from bigger to smaller. All right, so we deposited all our sand here. We should have mud next. But I don't know what's in the Toroweap Formation, and I'm not going to take a moment to Google it right now. If one of you wants to Google it while I'm talking, please feel free. And then we go to the environment of an offshore marine environment. So what we're actually seeing here at these contacts are environmental changes big enough to change rock types. What we're seeing is the ocean, the shoreline going in and out. All right. we're seeing what most of the people in Florida and just about anywhere else in the South are absolutely denying does not happen, is that sea level changes. Okay? It's mind-boggling. And this is why we do just sometimes shake our heads. What they're really arguing about, and they just don't want to admit it, we hardly ever talk politics in here, so give me 30 seconds. What they're really arguing about, and just won't or can't admit it, is that humans are responsible for it. And again, that's, that part is touchy. I get it. But to sit there and say, as your streets are flooding more and more and more, especially as a mayor or a governor or a senator, that no, this isn't a thing. They can't be that stupid. And it's not Republican, it's not Democrat, it's not that kind of political. It's just, it's crazy when science and politics get mixed up. It's horrible stuff. Did anybody Google Torley? No. Okay. Well, it's either going to be sandstone and limestone, or to make my Sesame Street version of this story true, there should be some shale in there somewhere, but I really don't see any shale through those shrubbery. But so these contacts, at any rate, are environmental changes. And when and if we do the geologic time chapter, you'll learn a lot more about contacts, unless I'm forgetting that it's in the next slide or two. And it might be. Yep, so here we go. So a contact is a boundary between two different formations. It represents a change in the depositional environment. We just said that. It may also, and this is the big part, it may also represent a gap in time. We really don't know how long there was until we go in and take samples and send them off to the lab between the Coconino Sandstone and the Torweep Formation. That line there could be a couple million years. Remember, things like sea level change and whatnot don't just happen like that. It's a slow, gradual thing. Also, you could shift to a weathering environment. Think about the cover of your lab book, right? That's that little falls exit there, just down the road. And those rocks are, I always misquote it, and it's my own picture, I should know. I'm going to say 380 million years old. It might be 4 something. Let me look. I got my lab book here. 450 million years old. So that shale is 450 million years old. It was deposited 450 million years ago. What's on top of there now? Soil, some trees, some shrubs, whatever, right? So let's say that Al Gore and Woody Harrelson and all those folks, Bill Nye, are absolutely correct. And in the next 100 years or so, sea level is going to completely rise. We're a bit far in for this conversation, but sea level was here before. We know that because you're surrounded by limestone. And boom, we turn back into a depositional environment. Now jump another 10 million years into the future. We still care about stuff like this. Ideally, there's another version of Mohawk Valley Community College sitting here, and they're studying geology. And that lecture teacher has a picture of the new Little Falls exit on their lab book. There's going to be a gap from that Utica shale that's there to whatever this new, we'll call it the Nye limestone. All right. There's a gap there that is going to show little to no evidence of 450 million years plus or minus a handful where it was just glaciated and soils and so on and so forth. So just looking at this, yes, rocks equal time, but you have no idea what was erased until you actually get in there and start poking around. So those seemingly benign little black lines there are actually possibly the more important part. Just something to think about. That's called an unconformity. Yet another vocabulary word for you. So it's a gap in a rock record, which therefore equals a gap in time. And it could either be due to a weathering event or just the fact that you're in a non-depositional environment. Right now, we're in a weathering sort of environment where we are right now. Mother Nature's doing her thing. People are doing their thing, going through with dynamite and giant diggers and everything, building Walmarts up here and there. Sorry, I usually say throwing up Walmarts here and there. We're definitely in a weathering kind of time period. But certainly there's some areas where we're creating rocks, other places on the planet. Not to mention all these landfills full of plastic and tires that we're making some kind of cool new rock out of, I'm quite sure. So unconformity, yet another vocabulary word that is surely going to be on your test. So, like I said, rocks equal time. All right? The beds, equal time. And if you think about it, the beds were exposed to the surface for sedimentation to occur. And yes, in this conversation, the bottom of a lake or the bottom of the ocean floor still counts as the surface of the earth. And because that was the surface of the earth for some amount of time, life was going on in it and around it and on it. And when we're lucky, some of that gets preserved. So not only do rocks equal time, but as I said, oftentimes they are some pretty cool photographs or snapshots of time as well. If you know what you're looking for, you can go back through and start piecing stuff together. And I've been very slowly introducing you to this idea. We started with a lot of those lava features, saying, well, we only get this to happen in this environment. We only get that to happen in that environment. Remember that conversation? So we started introducing that idea to you, and then it turns out the whole world of sedimentary rocks is nothing but that. And believe me, a rock is a rock is a rock. I do not get excited by looking at rocks. But looking at the bigger backup picture, the environments, the outcrops of a rock is totally different. And unfortunately, we got to go through that stupid stuff in lab where you got to go around and say, oh, this is a hunk of this. Oh, this is a hunk of that. Oh, this is a hunk of that. You got to get past that in order to figure out what's going on. So that's why we do that to you guys. I know you aren't geology majors, but for the non-majors, we're just hopefully teaching you to get through something you don't like doing because you still got to do it. But hopefully you'll pull a little bit more out of it than that as well. Like I said, this is something you are surrounded by for the rest of your life. If you are out, moving around in cars, visiting the planet, and so on and so forth. Maybe some of this will stick with you. All right. I have been talking for damn near an hour now, and we're actually getting into some fairly heady stuff where I want you to think and apply and whatnot. So I think we're actually going to pause for the day here.